there, welcome to our video. Today we're going to be talking about power issues in computing. I'm Morgan and this is Cameron.
Hey there. And more specifically, we're going to be talking about why we even care in the first place. In addition to that, we're also going to be looking at how a CPU consumes power and also the effects of that consuming that power on the CPU, mainly in terms of performance. And lastly, what we can do to moderate that power and yet still retain our performance. But first, let's take a look really quick at why we even care in the first place.
So why do we care? Well, using power costs quite a bit of money, and with more power being used, of course, the more money you're going to have to spend to get that power. And it's not just about the money either. It can kind of be a little bit related to kind of how we get that power in the first place with environmental concerns. If we're not really generating power in an environmentally friendly way, then using a CPU that uses more power can kind of tax not only your wallet, but also the world in general. And if you looked at energy bills recently, you can kind of relate to that. So with 15% of the global residential electricity consumption being due to consumer electronics and computer equipment, it's no real surprise that we're kind of trying to limit our power usage. And it's not declining at any time because, of course, with such a technology-driven world, that's just only going to go up as time goes on. And of course, power and performance are related with the CPU, as we will discuss later on, and with a higher desire for performance, with a higher clock speed and things like that, the demand for power must be met as well. But of course, with this demand for power comes a warmer chip, and we'll also be needing better cooling for such CPUs that use a lot more power.
So now we're going to move on to how a CPU actually consumes power, talking about mostly the transistor part of it. A large portion of the power, around 95%, is used dynamically to switch transistors on and off, which is what we refer to as dynamic power. This is the power to actually charge transistors to capacity. The energy drawn from this power supply to charge a capacitance C to voltage V is C times V squared. If the voltage on the capacitor switches at frequency F, or F times per second, then we can calculate the dynamic power consumption as P equals half of F times C times V squared, since discharging does not draw energy from the power supply, and therefore only half of the time uses that power. This can also be multiplied by an activity factor, since the transistor itself isn't being used 100% of the time. A smaller portion is static power consumption, or leakage. Systems draw current even when idle. Even when the transistors are off, they leak a small amount of current. This static consumption for a transistor can be calculated as P equals I times V, where I is leakage current and V is voltage. So let's take a real quick look at how clock frequency and power consumption is related. We're often interested in getting a higher cycle count per second. So if our clock ticks faster, assuming other things being equal, we're getting more done. This comes at a cost though, and not just in terms of design trade-offs. We can look back at our equation and see if we increase the frequency at which we flip a transistor, it's going to consume more power.
We can think of this like an actual analog clock with hands. Imagine the minute hand revolving a full 60 minutes. In one instance of a CPU, the 60 minutes worth of work might be done in, 60 minutes. However, in another CPU with a faster clock, that same 60 minutes worth of work, so a full revolution of that minute hand, might only take about 45 minutes. Or, given the full 60 minutes that the first CPU had, the second CPU with the faster clock would complete more work in that given time. Because our clock is now faster, we're going to use more power.
So we can see that quite a bit of power is going to be needed if we want to keep up with our performance drives. Now, looking back at our equation, there's going to be some key ways that we can reduce this power consumption. So since power is proportional to the V squared, then if we reduce V, then we're substantially going to decrease the amount of power consumed by a CPU. So there's some problems with that, which we'll see later, and given the fact that we're also going to be probably making the clock speeds faster, the V squared can only really be brought down so much, and then the frequency starts to negate the effects of driving down the voltage in the first place. So some problems with scaling down voltage begins to arise when we see that the voltage deals with what we call a threshold voltage. So a transistor has a threshold at which it will be counted as a 1 or on and a 0 or when it's off. Or if we lower the voltage, then the threshold voltage at which it would be considered a 1 would also be lowered. That wouldn't normally be an issue with all things not really without that many outside environmental factors. However, there's quite a bit of noise in the system. And so the noise that would additionally or previously have affected the CPU with, say, maybe about a volt, it wouldn't be such a big issue if the threshold was somewhere around the 5 volts, for example. However, if now all of a sudden you reduce your voltage to 3.3, then the noise that still has the effect of around 1 volt, making it waver at least 1 volt, would start to have a lot bigger effect on this CPU than it did on the CPU that used the 5 volts.
These techniques can only get us so far. Other avenues must be explored, such as switching off parts of the CPU that aren't in use. For example, the register file isn't typically accessed in each cycle, at least in some types of circuitry. And in many cases, the values of particular registers need not be updated every clock cycle either. In light of this, it is beneficial to gate the clocks of these registers. This means that we can temporarily turn off or cut current to circuit locks that are not in use. In addition, a similar method can be used to power down arithmetic units that aren't being used in a particular clock cycle. An example is a branch that probably won't use the multiply function. Similarly, CPUs often are waiting for inputs from peripherals and power gets wasted. To reduce this, CPUs are now provided with a hierarchy of power states. Each state defines a certain level of activity on the CPUs and a certain time penalty for it to get back into a fully active state, which is one of the costs that is often associated with saving power, and that is performance. Memory and I/O devices often have similar power states. It is the system power management mechanism that monitors the system activity and enforces the movement of the system components between different power states. Another way to help reduce the power consumed is by redesigning the cell libraries, or the low-level arrangement or collection of low-level electronic logic functions like AND, OR, and NOT. Power savings can come from 2 sources here: device sizing and restructuring of the logic and physical layout of the cell. Device sizing, for optimizing switching energy versus delay, ensures that we sacrifice a minimal amount of performance for a relatively substantial amount of power saved. It is also feasible to schedule tasks based on how hot or cool they are. This is significant because a CPU warms up more with some instructions than with others. When it warms up, we often use power to cool the CPU down. To help reduce the power needed, we can balance out or schedule tasks so that the hot and cool tasks are appropriately placed to prevent the CPU from heating up too much, therefore reducing the amount of power necessary to cool the CPU. Another technique that can be used is to move a task that is on a hot processor to a processor that is cooler, helping eliminate the need to spend more energy on one processor. Many of the techniques we've mentioned so far are in regards to the hardware. Software-based power reduction is also a valid way to help curtail the power used overall. A classic example of this is a busy wait loop. Consider a spreadsheet that requires frequent user input. When the spreadsheet is recalculating values, high CPU activity is most likely desired in order to complete the instructions in a short time. However, when waiting for the user to type in values, which arguably is a long time in computer time, a busy wait loop will prevent the CPU from entering a low power state. The power wasted is pretty substantial as well. A 166 MHz Pentium processor with MMX technology draws over 7 watts in normal operation, but only 1 watt when halted.
However, with most things in computer architecture, this introduces trade-offs with some of the things that we're trying to do to help reduce the power consumption of a CPU. So adding in these features such as the delays or the gating of certain parts of the CPU introduces some time that we need to wait for safely powering down and powering up these parts. So this could hinder the performance of said CPU quite a bit. And depending on the extent of how much we would like to save power, which in some cases would like to be quite a bit, for example with mobile devices, then we can actually severely hinder a lot of the performance that we gain just by, for example, like we said, powering down certain parts of the CPU. The aim is to reduce the power consumption as much as possible without really taking down the performance by that much. In addition, these techniques, at least the ones, for example, provided before, such as switching off certain parts of the CPU, really only tackle the leakage problem, which doesn't really compose a significant part of the amount of power consumed. For example, the dynamic power that we talked about, which is actually switching the transistors from off to on, that's a large chunk of the power, and only switching off parts that aren't in use doesn't really help with that much. Doesn't really help that much anyway. So, for example, reducing the number of transistors used would help with the dynamic power consumption, but there's reasons why we are putting more and more transistors on chips these days, and so that really isn't a viable solution. And there are also other reasons, such with, for example, taking the transistors and reducing the transistor count, that we can't really get around that because sometimes there's just a base number of transistors that we need. Much like, for example, there's only a certain amount that we can lower the voltage to and still have it effectively work in our CPU.
So today we talked a lot about power issues in computing, mainly why we care, how a CPU consumes power in the first place, and in addition to that, the effects of power on a CPU, and finally what we can do to moderate that and yet still retain that performance.
If you'd like to learn more about these issues, you can follow the links below. Thanks for watching.
Thank you.